Thanks a lot for the invitation. It's always a pleasure to be here at PI. I think it's one of the places where one also feels home when in foundations, because sometimes one has to justify one's work if one talks about foundations, and this is not needed here, I think. But this work I'm going to present today is maybe more a kind of mathematical or technical result that actually came out of research in foundations, but probably could also have other applications, for example, in quantum cryptography. But I'm not going to talk about that part, because in particular, those who attended the workshop, which just took place on Monday, Tuesday, and Wednesday, already heard about these connections. Okay, so specifically, I'm going to talk about a result that is in a certain sense an extension of a result by Tsirelson, but the extension goes in a direction which is different from the usual things where people consider infinite dimensions. So we are still basically in finite dimensions, but extended to a more quantum version in a sense that I will describe. And I should also say that the work is joint work with Ramona Wolf, who incidentally is also here. So if there are very difficult questions, I may defer them to her. Okay, so let me just write this title, but the title, as you will see, is somehow neglecting an important aspect, because I will also tell you that not that all commuting maps factorize. So as you already know, for example, from Tsirelson's problem, we, for example, need to make an assumption about dimensions. And in this case, there will be some additional assumptions needed, which I will try to motivate and so on. So what's the general setup that we are considering? So we assume we have a big quantum system, kind of global system that has a priori no local structure. And I call that system K. So you can think of this as being modeled by a Hilbert space, but I assume whenever I'm not specifically telling you otherwise that this Hilbert space is finite dimensional. The dimension can be arbitrarily large, but I assume it's finite. And then we have two agents, Alice and Bob, who perform operations on that world that is modeled by this Hilbert space. So there are some interactions, so they may give some input to it and receive output, and I will just model that more precisely. So this is only the kind of overall kind of illustration. I will describe this in a minute in terms of trace preserving completely positive maps and so on. But the idea is Alice may give some input into the system or do some action that depends on some input I, and then receive some system, some information out of that. Bob may also input some information that I will call J and receive information from the system that I call B. And the kind of motivating question is we would like to find conditions that allow us to equip this system with a local structure, in the sense that we can somehow say there is a subsystem, which we could call K prime, and maybe another subsystem that I will call prime, K prime prime, and I will tell you the reason why this is not Ka and so, but these are just two subsystems, such that we can describe everything that's going on or the operations that Alice performs as operations that act non-trivially only on that part, and similarly for Bob, they act non-trivially only on that part. So the question is, what are the conditions on that? Okay, so that was the maybe general introduction, and now let me describe what I mean by this picture really. So I will consider it. So maybe I should first also say that this setup can be generalized in many natural ways to, for example, more agents or interactions where they act more than once. But I will, for everything I say here, stick with two agents and an interaction where Alice just gives one input and receives one output from that system. So therefore, I could say that what Alice is doing should be describable by a completely positive map, a trace-preserving completely positive map, that acts somehow on this system K. So one input to that map is the Hilbert space K, and of course there's also this input that Alice chooses. This is kind of the thing that she really controls, or that she acts on, or where she can prepare an arbitrary state, for example, on this system I. This as well is just an arbitrary finite-dimensional quantum system. And then the output that Alice receives is as well a system. Here, actually, the dimensionality is not even important. And the system K, of course, still somehow exists. And so there may be some change on the system K, and so we want to keep track of that. Now, similarly, I can, of course, write down Bob's operation. Now I no longer have to explain this. So he acts also on this big system K, and his input, as you saw here, was called J, and the output was called B. And now the question is basically, under which conditions can we write these operations as product, and under which not? So a priori, because we don't have a product structure on K, the order in which Alice and Bob execute their operations will matter. So we have to assume that we can consider a setup where, or the case where Alice acts first. So in that case, I would basically write these two operations. I will now make just a smaller picture. So that's X. I will do that first, and then Y. So basically, the K system here goes through in that order. So I could have drawn like a connection from here to here. So that's one possible situation. So then here we have I, and here J. And here we have the output A and B. Or we could do it in the other way around. So in this case, I would draw it in that way. So these are just the orders. And clearly, in order for this to make sense, because this is the same system, so I cannot a priori apply that in parallel, I'll have to draw it in that way. So here again, I have the output A, here the output B, here K, and here is the input. Now, clearly we would expect that, I mean, if there is a chance that we can say this operation only acts non-trivially here and this one non-trivially here, the order shouldn't matter. So clearly, if the order of their operations matter, we have no chance to somehow make a statement about this factorizing. So we will certainly have to somehow assume that these two situations lead to the same overall behavior. So the way we could now just say this circuit diagram again defines a map from IKJ to AKB, and this one as well. And we could in principle say a reasonable assumption that we even have a chance for this factorization is that these two maps are equal. So by writing this equality, I really mean the overall map. So I compose them together and then have a new trace-preserving completely positive map. Actually, it will turn out that this will be a too strong requirement for what we are going to do, and I don't need to even consider the output here on K. So in a sense, you can say what will be sufficient for our goals will be to say that the behavior that Alice and Bob see, like the A and B, depending on the I and J and on the initial state of the system is sufficient. We don't need to consider the final state of that system. So that will be an assumption, and I will call this assumption the commutation assumption. Okay, so that's basically the left-hand side of the title. So we are asking what about so when I talk now about commuting maps, I mean that thing. The maps are X and Y, and the commutation means that with this trace over K. Now, what do we want? What do I mean by this red factorization? What I would want is that the two maps somehow act as products on separate parts. So I would hope that there is an input which is just one part of K, or maybe I should make this red now to match the picture. So there's this red part K prime, and here the red part K prime prime. the map still takes an input A, and here, I, and produces an output A, and here it takes an input J and produces an output B. And okay, at the end, of course, these maps, so if they are the same maps, so actually we want to talk somehow about the same maps, they will also produce an output K here. And if I write it like that, it has to be the case that K prime is somehow isomorphic to K prime prime and isomorphic to K. But this is just a somehow, okay, this now doesn't yet reflect the picture, because you would say, okay, how can these be subsystems of K if they're equally large? So the idea is the following, that I would say this factorization is modeled in a more general way by some map, which is also a trace-preserving completely positive map that I call D, which takes as input K and somehow distributes the information in K to two systems, where formally this system K prime is as large as the original one, but only gets information that is relevant for the left side, and that one only information on the right side. So at the end you can say this map D distributes the things that are relevant for Alice, to the K prime system, and the things that are relevant for Bob to the K prime prime system. And then once I've done this distribution of information, the maps can now act in parallel to the two systems. So that's what I would mean with factorization. So I call it this fact. Of course, if you like, you can write this in a different way and say, okay, because this information is distributed to the two parts, we can somehow potentially make these Hilbert spaces smaller. But the actual technical statement will be that this, the product space here, K prime, tensor K prime prime, is somehow embedded into K. So there is a map that I will just make more precise in a minute. But this space is somehow connected to that via an isometry. I will just write this more precisely. So that's now everything I need to phrase the question. So the question I would like to ask is this commutation here sufficient to imply the factorization for some D? So by factorization, I really mean there exists some appropriate trace-preserving completely positive map D such that this thing here, which let's say I abbreviate that by, let's say this is a new map that I could just call E, calligraphic E, which goes from IKJ to AB. Can I write this map E in this factorized form?
Are you tracing over the K's on the...
Ah, yes, thanks. I should not forget to trace over the K, yes. Thanks. Okay, so commutation means I have equality from here, and factorization means this thing which is now equal is also equal to this factorized way of writing it. So the question is, does commutation in that way imply factorization? So remember, K is finite dimensional. This will be important for what I'm going to say. So that's still a question, and it will actually not be true. We will have to add an assumption on this side.
Could you ask this question both where the commutation includes tracing out K and then the map includes tracing out K, but then you could ask a different question, which is what if you know that there's commutation even if you don't trace out K? Mm-hmm. And then would you draw a stronger conclusion?
Yes, although in that case, one would, I don't know the answer to that question, but of course, and what we need to keep in mind that if you do that, you will have to, again, somehow recombine these Ks, because now the natural thing that happens is that the information at the end on the K system is also distributed. So you would have, a conjecture could be that, for example, the inverse map D would again recombine them. But there is something in this direction that we already know is true, because if we generalize this setup to more than two agents, then you could imagine now there's this staggered trace, there's a map X, a Y, and then a Z, and so on, and they all reuse the same K-system, in a sense. So the K-system is used further, and then if you assume commutation in, the natural generalization of commutation, that the order doesn't matter here, then the statement still holds, still when you trace out K, but the K-system is now, in this case, still reused in further steps, in a sense. So in that sense, it's already pointing in the direction that this should be true. So in a certain sense, if you further use the K-system for additional questions and then compare the behavior for these additional questions, it's still true. So this suggests somehow that what you're saying should be true. But it's a good question, and I don't have a formal statement for that, but I would, because of that reason, because I can basically add stuff, suspect that this could be, there's a good chance this could be true, but I don't know. So, okay, is the setup clear? So this is just now the question. Now, what do we know about the answer to this question? So one natural special case is if I is just a classical value, so, and A as well, and similarly J and B. In this case, this corresponds to something extremely familiar. It's something that occurs in all Bell setups and so on. So this is now a big system like the quantum state. In a Bell setup, it's what we think is the entangled state. In a kind of device-independent setup, we may not know what the state is and so on, but we would know that Alice chooses a measurement in this case. So I would be an index that labels a measurement that I would like to execute, and A would be the classical outcome of this measurement, and similarly here for that side. And then we are in a very familiar setup that I think has been studied very extensively, also here, particularly in the groups here by Rob, and I will not maybe go too much into that, but just briefly mention the connection to what we know there, which is basically Tsirelson's problem. So the first statement I would like to make is, in a special case where I, A, and J and B are classical, this is a problem that has been studied very extensively, in particular also in Waterloo, and very important contributions have been made here, which extend to the case where K is not finite dimensional, where this problem really becomes very hard to tackle. But I will stay with the finite dimensional case. So what precisely is this connection to the Tsirelson problem? So as I said, it's first of all, I, A, and J, B have to be classical. And now I could say, let's suppose we have two sets of measurements. So we have for any, so I will now use small letters for values of these. So I and J are now random variables, if you like, and or you can think of quantum system in which we encode a classical value, and I will denote the classical value encoded into that system with a small letter I. So for any I, we have a, let's say, I mean, this can be generalized, but I think this is already general enough. We could have a family of measurement operators, and the family has the index A, which defines a projective measurement. So in particular, we would have the sum over A is equal to the identity here. And of course, we can do the same thing for J. So that would be the measurements that Bob would apply. And a priori, these should be operators on the Hilbert space K, on the total Hilbert space that a priori doesn't have any structure. So maybe I'll write this here by putting the index K here so that you see it sums up to the identity on K. And now I could say the map that Alice carries out is the following map, X. If I give to this map as the first input, as the input I, this index I, and as the second input some state on the system K, then I receive as an output basically the outcome of the measurement, which I encode as a value A in the system A. And of course, I still get the measured quantum system back. So the measured quantum system is just the operator applied to, the projection applied to the system. So that's what the projective measurement does. And if you want to consider an arbitrary POVM that works as well, then I would just have to write square roots, and I didn't want to clutter the notation. There's nothing different otherwise. Okay, so this is for Alice, and of course I can write the same for Bob. I will not write this down, but you will, of course, notice that here is a B and so on, and here are the projectors P, B, J. So these are now examples of maps. And in this case, the commutativity relation is equivalent to just say that the measurement projectors commute. So in this is of course now a special case, obviously, but the commutativity conjecture, the commutativity assumption in this case is easy to see that it's equivalent to just the statement that for all I, J, A, and B, the measurement operators commute. And both directions are easy to see, because obviously if they commute, then these maps, which are defined basically in terms of these operations, I mean, this is the only place where they act on the same system, commute as well. And conversely, if this is true, you can just rewrite things a little bit to bring the commutators together and use the fact that this is true for all rho, and then you will find that indeed these operators commute. Now, the independence assumption in this case can also be written in a particular way, which is more familiar maybe to some. So if we ask ourselves what happens here, we can say that once I trace out the system, so okay, what I get if I apply both maps is something of the form I have the outputs encoded somewhere in these systems. So these are the outcomes of the map. And then because the independence assumption is such that I trace over the case, I'll have this trace here. And the trace is now over K and K, over K prime and K prime prime. And then what happens is the following. So I first have the doubling map applied. So the independence assumption tells me first apply this, or doubling this D, I called it doubling map in the paper, but here I just said it's a map called D. So this map D first splits the space in two spaces, and then the measurement operators pi here, they now act on the two sides. So the measurement is basically a pi I A, but this now acts on K prime. So the doubling map has K prime as an output, and there is another map B, J, which acts on K prime prime. And that will basically be the output of the map. So this is what happens if I apply this total E. So if you look on this side, the E on input I, J, J, and the E already includes the trace over K. Okay, so this is just to write this explicitly. So basically I just took this circuit diagram and inserted these definitions for the maps, and then I get this expression. Now, if you look at this expression here, this is a trace-preserving completely positive map. So let's briefly consider this a bit more closely, but what's going on here. Now, we know that a trace-preserving completely positive map can always be purified to basically an isometry. So I can equally well write this red expression here. Okay, I shouldn't cover this camera, but okay, let me. So this red part here can also be written as a trace. So the trace goes basically over everything that is here, so I don't need to specify that, of pi AI tensor pi bj. And now if I take the spine spring dilation of this completely positive map so that it's an isometry, I get an additional system which I call the R system, and then V should be the dilation of D. So the idea is that the map D, the completely positive map, can be written as a V dagger, and then a trace over R, which is included in this trace here. So this is a different way to write this. And then once I have this form, I can, of course, also pull this V over on that side. And I can also, if I want, just to make that point that I want to make, say, I define a new map pi bar, which includes this identity. And then you see now that what happens is that this thing here is an operation that pulls back this product measurement onto the space K. So this is an operator on K. And this is what I meant by this little arrow here, so in a sense. So the product operation is somehow embedded into K via an isometry V. So in a sense, I can say this is just what we usually do. And that's basically now Tsirelson's problem. So the statement that this is equal to what we get by executing the maps in a sequence is Tsirelson's problem. So if I put here, if I require here that this is equal to the trace of pi, let's say IA, applied after pi bj on rho, k, then, I mean, this is on the original space K, then this is kind of corresponds to the independence assumption. So what I've said now, so in case this was too technical, let me just summarize this last point. What I did is now to say, if we consider the classical case where x and y are just projective measurements, then, the factorisation assumption. So if we insert these measurements as the maps x and y, then the factorisation assumption, the assumption that the E map, so this thing can be written in that way, corresponds to the statement that these projective measurements, which act in a sequence on a system K, can also be written as product measurements. And that's a known result, a very well-known result. That's a result that has been proved by Tsirelson and actually extended by many others. There's a nice paper, for example, by Volker Scholz and Reinhard Werner, which says that even in certain cases, for an infinite dimensional K, we can always find such an isometry which allows us to split this space K into two, such that the measurements factorize. But we also know from recent work by a group of people, including, for example, Thomas Willig, that this cannot be true in full generality if K is infinite dimensional. That's another very well-known result. So, as I said at the beginning, we are in the finite dimensional case, and the fact that this is a well-known fact about this classical case suggests that maybe this question that I asked here could also be true in this quantum generalization. So, the special case that I described here, this implication in the special case, is Tsirelson's problem, which is known to be true. And the question is now, is this more generally true? So in other words, the question I asked is in a certain sense a quantum generalization of Tsirelson's problem in the sense that this I and A are no longer classical variables, but quantum systems. So this is the way one could phrase the question. Is Tsirelson's fully quantum version also true? Yes.
Just wanted to get one thing clarified. When you introduced the independence assumption over on the board there.
Yes, maybe I should say. Yes, sorry. Thanks. I somehow should be consistent with the title and write factorization. Yes, sorry, that was confusing. Yes, I always meant the factorization.
Can I ask another question about the bottom board, the one came down on just
this here?
Yeah, just kind of for my intro background. I mean, I was reminded of this Beckman et al. Paper on semi-localizable and semi-causal maps. Is this result, the fact that you have this implication in the classical case, it also implies, I guess, that you could not implement, for example, the Pierre box functionality with two gates x and y that could, you can't find two gates x and y that could implement the PR box functionality in either order.
It's great you asked this question because this is a perfect transition to the next part of my talk. I'll now talk about the PR box functionality.
Say it again?
I will now talk about the PR box functionality. Yes, this is an excellent question because that's should immediately, I mean, if you ask, can this be true in general, or what's actually potentially going wrong in the general case, this has to do precisely with your question. So you put the finger on the right spot. Yes?
Sorry, can I just ask about the dimension of the systems of IDR and V? So what is the R of IDR?
Ah, yes, sorry, I didn't. So the idea was that if I have a completely, so about D, we just know it's a trace-preserving completely positive map. So we have D acting on some system P. Now what I'm saying, I write D in terms of a Stein spring dilation, which means I have an isometry V, which I let act on P. And now this V is basically, so for some V, which goes from, so the map D goes from K to K prime, K prime, prime. The V now goes to from K to K prime, K prime, prime, like the map D, but in addition to some extra system R over which I trace. And R is just this extra system over which I have to trace again. Yes. So actually what we will see is that the PR box is precisely the reason why, I mean, you could imagine if I put here, or I said at the beginning, this is not going to be true in full generality. And the PR box is precisely the one example that shows that this can just not be true in full generality without imposing additional assumptions on this side. Now maybe the potentially confusing thing is that the PR box is classical. That's probably why you look like that. So indeed, the PR box is classical. I mean, in the sense that it has completely classical inputs and classical outputs. So the point will not be that if we just move to the classical case, we have this result is true. So this result was true because we actually did more. We moved to the classical case, and in addition, I said these are projective measurements, or more generally POVMs. But now, even classically, you can, of course, do more than just apply POVMs. I mean, POVM is just one way to model a measurement which somehow changes the system in a minimal way, in a certain sense. Of course, I could, for example, have a projector on the system that, after projection, rotates whatever I did. So actually, something which is, in a sense, implicit to, I mean, implicit not in a mathematical way. So Tsirelson is, of course, very explicit. But if you just write it in that informal way, like, and say, Tsirelson's problem is the classical version of that, then you haven't said everything, because it's extremely important to notice that the way Tsirelson models measurement is as projective measurements and not as general measurements with some instrument that arbitrarily can change the state. So that's maybe one of the most important messages of this talk, that Tsirelson's problem actually imposes a restriction by talking about, in that case, Hermitian operators. That's a very important ingredient to the proof, to the correctness of the statement. So one could say that if I just want to ask the question, is this true if I just apply measurements and I don't specify, then the answer will be wrong. And it's only true if I say it's true if I assume commutativity plus the measurements are projective, or at least Hermitian, or it's a POVM and not more. And the way it acts, the POVM acts is like the square root of the POVM element on the state. So this has to be imposed. And because it really, the fact that this is not true in general has nothing to do a priori just with the quantum thing, apparently. But it's then the question, how do we model that thing quantum mechanically? Because quantum mechanically, they are not measurements.
Is it really like, does the particular update rule matter, or is it just that the basis of the measurement, which would be I, when you forget about the output of the measurement, the state after measurement is the same for all I?
I think the important thing is that, okay, let me maybe write, if I have a state rho, and normally if I look at POVMs, I'm of course just interested in the probability of the outcomes, and that's why these questions don't matter. But if I really want to know what's this, if I consider the update rule, let's say I have a POVM with, let's say, POVM elements n, which I could now also label n MIA, just to be, they're, instead of projectors, POVM elements. Now I would say the post-measurement state conditioned on the outcome A is up to a normalization factor, which is of course well known, is the state MIA square root acting on rho MIA square root. Now, it's important that I really put that in that way, because in principle I could take any, so in principle I could say I take here, I add here an arbitrary unitary that depends on I and A, and here as well. And that would be another valid way to model the measurement, which, as long as I only consider the output distribution, would be exactly the same. But if I look at the state after the measurement, that will of course be a different state. Now my point, or the statement I would like to make, is that Tsirelson's Tsirelson's answer that commuting measurements factorize is only true if we model the measurement updates without this U. I mean, where the U is an identity and we just have the square root of the measurement. I mean, it's maybe not true only then, but if we have to impose some constraint in addition. So it is true if we do that, then we know it's the true statement. So this is somewhat, if one talks informally about the problem, one may tend to forget that. One has to say the measurement is modeled, the update rule is that particular update rule, and if I impose another update rule, it may not be true. So yes, so the update rule is important. I'm not sure this answers precisely your question, but okay.
I'm a bit confused why this makes a difference, because you trace out the system.
Yes, so right, if I was only interested in the probability distribution of the outcomes, then this would not make a difference. However, in this case, I'm not, because in this scenario, still for, like, this is the first measurement, and of course, how the second measurement, I mean, at the end, I'm not interested in K, but of course, how the Y behaves still depends on what was the updating rule applied by X. So that's basically the answer to also your maybe very important question. So in a sense, for X, we cannot just model the measurement just by a POVM, or we have to make this explicit and say, if we use POVMs, we are not only interested in the probability, we're actually interested in the post-measurement state, so we have to make an assumption there. And the assumption is that thing, that this U is not there. So,
Renato, so this is the Luder state update rule. Mm-hmm. Is that something that was known previously, that, you know, in the case of finite-dimensional K, mm-hmm. commutation implies factorizability for POVMs that have Luder's rule state update, or was it only known previously for projective measurement?
No, I think this was also known for the general updating rule, yes. Okay. As far as I know, yes. Yes. I think it's also not, as if I remember correctly, but I have to check that, to prove one from the other is relatively direct. So it's not, one doesn't have to redo the whole proof. I think one can do it for one and then somehow extract the statement for the more general POVM elements from that, if I remember correctly, but I have to check that. I'm not sure. Maybe someone knows here, because I guess there are some experts here on Tsirelson's problem.
Is it connected through the Neumark dilation somehow? That if I dilate this POVM?
Yes, probably yes. Yes, I think so. But I mean, modulo some wrong memory I have. But at least this is seems not to be a big discussion. So sometimes people state it for projective measurements and make the remark it's also true more generally, but for simplicity with them. Also, sometimes it's stated in terms of Hermitian operators which encode the outcomes, and that's again a different language in a certain sense. But that language, of course, implies somehow the projective rule, because, yeah. So, yeah, the update rule is apparently very important. So that's maybe why I said this title doesn't capture anything. One has to say commuting plus the right updating rule implies factorisation. That's already true for Tsirelson's problem. Now the question is, I could now say for Tsirelson's problem, we know the answer, the updating rule has to be this. I mean, that's well known, that's nothing new. Maybe, I'm not sure how many people looked at it in the more general case and then just said, oh, it's not interesting because it's not true. But for Tsirelson, we have to make this assumption. The question is now, what is the generalization of this assumption to the quantum case?
Did you mean what you just said? That I thought in response to Ellie's question, you said you're not sure whether the Luder state update captures the only case where factorisation.
Yes, no, yes, right, yes.
So when you said it has to be this, you didn't mean that.
So it has to be to apply the current, yes. So, okay, yeah, let me be clear. We don't know, or at least I don't know in the classical case, what's the most general statement. Actually, I know something about it because for the quantum version, we have actually a tight criterion. And so one could then return to that in a sense. But a priori here, we know only that direction. If we use that update rule, then we know the statement is true. And conversely, we know that if we impose no additional constraint on the update rule, we know it's not true. And the reason why it's not true is the PR box. And okay, probably I'm not going now into I could go into the PR box at the end if people have questions about that. But basically the idea is that the PR box can be modeled exactly in that way. So I define maps X, which basically do what the PR box, how you would implement naively a PR box. You would just say, choose that A output randomly, and then convey the information about what the output A was, as well as the information what this I was to Y. And then Y just does the calculation of whatever the PR box. I mean, now Y has all the information. It knows A and it knows I, and it just outputs that. Now, the non-trivial part of this is that it also has to work here. But now the trick is to say, you just put a particular input here, one particular symbol, which tells the map you are the first map to act. So if the map gets that input, it does, let's say there is one symbol, let's say a 0. Whenever it receives a 0, it knows I have to randomly choose A and convey the information to Y. And of course, this information conveyed to Y is not a 0. It's a pair of values. And this map now knows, I'm the second map, I already received the non-zero, I'll just go to implement the PR box. Now you can do that for both maps. The X can act in the same way. Just now here knows I'm not the first. So you see, I can basically cheat I'm cheater in that sense, or overcome this thing in a very simple way. So this is the example. So this was maybe a bit fast for, okay, I see from your face you got it completely, but probably it was fast if you haven't thought about this before, and I'm happy to explain that afterwards in case someone is interested. But basically the point is, the PR box is something we can realize, and it satisfies this assumption. Now we also know, again from Tsirelson, that the PR box generates output distributions which cannot be generated by a setup like this. This is the so-called Tsirelson bound, because the PR box violates the Bell inequality stronger than if we measure on a Bell state. And the only thing you can do here is to generate some state and measure locally. So the fact that we can create the PR box together with Tsirelson's bound, which says actually you cannot reproduce the behavior of a PR box with this setup, implies that this implication cannot be true in general.
Just to clarify, so you can do the PR box even if I, K, J are classical, or only because now they're quantum you can do it? No,
this is already, that's also a good question, because it's important to realize all what I said here about this not being true in general is even true for classical inputs and outputs I and J, A and B. Yes, right. So it actually has nothing to do with the quantum generalization. But now the question is, of course, here we have here we know we know a condition which is sort of natural, which implies that which makes this true, namely that we use this update rule. Now if you go to the fully quantum case, where these are just some quantum inputs and outputs, the question is, what is now the right condition that implies that we can do this?
Maybe before you move on to that, can you clarify one thing in this logic, which is, I mean, usually in the setting in which you'd say, okay, the PR box shows that this implication doesn't go through, K would be prepared in a particular state. Whereas to show that I have equality here, I need to say something like, for every state I might put on K, I have equality. And therefore, over here, for every state I might put on K, I have that map equal this map. So I'm not quite seeing, like, you've got a very specific state you're preparing on K in order to tell which gate.
Right, yes, so right. So I have to do two things. First of all, I have to show that for any input here, the behavior here and here is identical. But that you can verify with just, I mean, for the procedure I explained, this is the case. So if you just tell this map, it already has to act in the way it does. Because what the map, I mean, basically the idea is if the map already, I mean, I can maybe go through it explicitly afterwards, but this is one thing you have to show. You have to show for any arbitrary input, there's a commutation. But now to the PR box behavior, it's sufficient if that appears for one particular input, because you want to show you cannot reproduce it by this setup. So it's sufficient to have one particular input which produces the PR box behavior, because then for that same input, this should also produce the PR box behavior, and it cannot. So the less trivial part is indeed to show that if I do this trick that I just explained, I tell the map which is first. What happens if I now give input which doesn't tell the map it's first? So that's basically the what I have to do.
Good, thanks.
Now, actually, I'm almost done with the talk, because I now only need to tell you what's the missing ingredient here, and then we can, I tell you maybe very briefly what the proof idea is, but this was all to build up basically the question. So the question is, what do we need to say here on the left-hand side in order to let this thing disappear? So let me do that, because it's actually a quite simple condition. So I want basically to have here to let this question mark disappear by adding something on the left-hand side. So here I have this commutativity plus something else. And something else will be actually a unitality condition. So unital means the following. Let me write this somewhere, maybe, maybe here, because I think this setup is now clear. So the unitality is actually a requirement that, of course, then in the special case of classical inputs and output, exactly corresponds to this update rule that I had here before. The condition is the following, that if I consider the map X, so this is only a condition on X, not on Y. I mean, equivalent, you could phrase it for Y, but you only need it for one map. Now this map gets an input I and the system K, and it outputs A and the system K. Now let's suppose we ignore A, in the sense, so this just means I trace over A, so this is now a new completely positive map from IK to K. And what I want is that if I give as input to this map, so maybe let's do it first graphically, I put here an arbitrary state sigma on I, and here I put a completely mixed state on K. So I just write this as the identity over K, because the normalization doesn't matter. Then I want that this thing just produces the identity on K. Okay, so that's the graphical notation. Let me write this also for those who prefer it in a different form. So it means that if I take this map X, I trace over A, so I don't even consider the output A, but I put in something arbitrary on I and the maximally mixed state on K, then I get the maximally mixed state on K. So somehow it means if I give the map as input something completely uninformative in a certain sense, in the sense of being a mixed state, then what it outputs again on K is something completely uninformative. So that seems to be already sufficient to now imply that. So that's the unitality condition. So the theorem now that basically the title hints at is, so now let's turn this into a theorem, is that commutativity and unitality in that sense imply the factorisation in that sense. So in a sense, this plus this allows us to say that indeed Alice and Bob's operations factorize on two individual parts. So that's basically the statement. Now we can discuss the potential implications, but yes.
Sigma is for any state.
Sorry.
Sigma.
Yes, yes. This is for any, right. So for all sigma I, this has to be true, yes.
And you only need to assume unitality of the effective map on K for one of the two gates X and Y, or for
yes, both? Only for one of them, yes.
It doesn't matter which.
Yes, exactly. Yes. I just put it for X. Now, okay, let me just make two remarks which are maybe important now for the discussion. One is there is a kind of converse statement. The converse statement says that if we have a setup of that type, then we can always find maps which are maybe not exactly identical to x and y, so maybe some x prime, y prime, such that these two conditions hold. So in a sense, whenever we have a setup where we have factorization, we can express it by commuting maps which satisfy this unitality condition. So this somehow shows it's also a necessary condition. Maybe coming back to this, but I don't know how it exactly translates into this updating rule. But in a sense, we know what the exact condition is. Now the other remark is, why is this unitality satisfied in the case of the update rule? And basically the unitality condition just corresponds to the condition that if we sum over the POVM elements, we get the identity. So in the classical case here, this is equivalent to say the sum over the measurement operators gives the identity. And actually, it's only needed for one of them. So I don't need to write this also for B, for the reason before. So this is basically what, if you want to show why does this hold for the maps X and Y, which I defined before as the classical maps, then it's pretty easy to see that it's unital on the system K. The point is, of course, if you measure a completely, the intuition is, if you measure a system in a completely mixed state with a POVM or a projective measurement in particular, then what comes out is again a completely mixed state. You don't condition on, of course, of the measurement outcome. It's just on average. It doesn't change to this. It doesn't somehow put weight more on something else than on something rather than something else. So this is an important property apparently of measurements, which seems to be crucial for Tsirelson's statement to be true. And this, of course, satisfied for the Lüder's update rule. So, okay, that already concludes basically the technical part. Now, what I could do, if there are interests later, for those who are, is I could tell you a little bit about the proof. But let me just say the following, just so you know what type of arguments are needed here to do the proof. And this is just a 1-minute summary. So what to do for a proof is you say, okay, this is a statement about completely positive maps. Now we can equivalently express any statement about completely positive maps by applying the Joy-Malkowski isomorphism and write down a state which somehow is created by having a reference, which is a certain copy of the input in a sense, and the output. So in this particular case, we would say, oh, sorry, now I've covered the camera. Yeah, okay, maybe I'll just write it here. So the state that somehow captures this is a state where I have the outputs, A, B, and some copies of the systems which are isomorphic to the input systems. So I just entangle the input to these additional tilde systems and produce the output with the map, and this is the state that somehow reflects that. Now the whole proof works via analyzing the properties of this state. And one important property that follows from the commutation relation, and this is the non-trivial part of the proof, I would say, or the main, let's say the core of the proof, is to say that we can now somehow find or if we analyze this state, we find that the commutation property com implies that the conditional mutual information between the inputs and outputs of Alice and the inputs and outputs of Bob conditioned on the K tilde system is equal to 0. So that's something we can show by a sequence of chain inequalities and stuff. And the unitality is also used for that part. So that's why this was really the non-trivial part. One cannot otherwise arrive at this statement. Once you have that, you can invoke a very powerful theorem by Hayden, Chosa, Petz, and Winter, which says that whenever this conditional mutual information equals 0, the state for which this mutual information was evaluated has a particular factorization. I mean, it's actually it's a direct sum of factorized states. And now, knowing that structure, you can now reverse engineer basically the form of the map, and you find that the map has this product form where this distribution map follows from the way that this state here factorizes. So this theorem by Hayden et al. Plays a very important role because it's actually the theorem which gives you the explicit form of that map. Although this statement by itself is, in many proofs, not constructive itself. So it doesn't mean it's constructive. But knowing that, for some reason, that, let's say, knowing the existence of such a factorization, we can conclude that such a map exists. So that's only the, let's say, very overall thing. So there are these three main steps. Write this as that, evaluate that, then use that statement to factorize this state, and then go back to the completely positive map picture. Okay, so that's basically the proof idea. Now, if you are interested in the details of the proof, there is a version of all this on the archive, and I'll just put here the number of this. So it's 2308 05792. Okay. And it also, by the way, contains the explicit PR box example for that. Okay, so let me summarize. So if we ask this question that is in this picture, whether separate actions of Alice and Bob factorize, in the sense that they non-trivially act only on factor systems, this is true, or one can prove that factorization under a commutativity, which is, however, not sufficient, but a commutativity plus a unitality requirement, which basically makes sure that somehow the information that flows here in this picture, this picture is clearly a kind of information flow, although it's clearly non-signaling because of this equality, but there's still something flowing here if you look at the PR box example. So this unitality condition constrains this information flow apparently already in a sufficiently strong way so that indeed the maps are somehow on completely separate subsystems. Okay, that's all. Thanks a lot for your attention. Thanks for the many questions.
All right, thanks a lot for the talk. So I guess we have some time for questions. If you wouldn't mind moving the board down in case, I don't know if the camera...
Oh, yeah, right, yes, sorry.
Yes. Video of the people asking questions. So anyone has questions? Nick seems to be very, very excited. So.
So based on your description of the proof, it looks like we can prove something slightly stronger than your factorization statement, right?
Okay.
Because you were saying that, right, you got the vanishing of this conditional mutual information. So I gathered that means that X is going to be acting only on some subalgebra of the operators associated with K, whereas Y is going to be acting only on the commutant of that subalgebra.
Yes, that's true, yes.
So it looks like we can take that picture over there, and we're going to be able to recombine those two Ks at the end that you traced out, because we're really only acting on subalgebra. So it looks like we should be able to untrace the Ks and then combine them into a single algebra.
So you're basically saying that the answer to the question I was asked before would be yes, whether it's true. Like I was, if I understood correctly, the question I think that you or asked was, is this also true? Like if we, potentially if we, I'm not sure. We probably have to add something because, for example, it may be necessary to have also now the unitality condition on Y, because now we are saying something about what comes out of this. Okay, I'm not sure, but so I agree. This is a good idea. We haven't done that. So actually, for the motivation to even look at that came out of, for us, this was a very particular statement. We actually needed to do something else. We are developing a framework to somehow describe correlations in space and time in a unified way. And this question popped up in that particular way. So indeed, there may be generalizations which we didn't need to answer that question, but the generalization you are now talking about is if we here want to say more about what happens on the K system, is this equality here even true if I don't trace over K? Yeah, that may be possible. I don't know the answer, but I suspect that if there is a problem, it has to do with the fact that we now only require unitality for one of them, and maybe one needs to somehow say that both of them are unital, because in a sense, the unitality condition is really important to somehow have some information about what happens after the map is applied to the K system, because this commutativity condition doesn't talk about the final K at all. So basically we know nothing about what the K could kind of be completely disturbed in different ways here and here, and then it's not fully. So that could be a potential obstacle. But maybe there is a very nice condition, for example, just to require that this condition holds for x and y, which would be a very weak addition, and then it may be true. Yeah, that's something interesting to explore. Yeah. Thanks.
Okay. Rob?
At the point of clarification, so the mutual information condition feels already strong enough through the Petz-et-al result to get you to your factorisation condition. I think I got that right. So when you write that the commutation implies that, don't you mean commutation and?
Yes, sorry, yes.
Okay.
Yes, sorry. I probably said it in words, but I forgot to write. Yes, so that was important. So the non-trivial part was really, here was also actually where we struggled a lot, because of course we didn't have that first and hoped to arrive at that, and it somehow never worked. We always got it only in one in the wrong direction. Of course, this is always largely equal to 0, but on the way to prove that, one actually proves something like some data processing inequality for conditional entropies, and they always went in the wrong direction in a certain sense. And then the unitality was crucial to avoid this problem. And now we know it was necessary, even in a sense.
Can you help me understand the unitality in the following sense? Like I can sort of, my intuition is that, yeah, commutation alone should have been enough to imply that. Why? Because, how can A and B correlated in these sorts of structures? Well, they can be correlated through K as a common cause, or maybe, how can AI and BJ be correlated? Well, maybe I has an influence on B, but no, it doesn't, because it has to be in both sides.
Right, yes.
And maybe JA has an influence on A, but no, it can't, because on the left it doesn't. So it's got to be through K, the common cause. But now you've conditioned on K, so I shouldn't have any correlations left. So that's kind of my just conceptual, why should commutation imply that? So what's wrong with that logic that I just described? Like, what am I missing? Why do we need to add unitality?
Yeah, to be honest, my intuition at the end came actually then from this information theoretic way of thinking about that, like how much information do these different inputs and outputs give about the other, which is maybe a quantitative way to express what you're saying, and then you somehow get some vague intuition. But I think the best way to really understand it is just to go through the PR box example, because there you see explicitly what's going wrong in a sense. Because what you're saying should already be contradicted by the PR box example. And there you see, in a sense, the information, of course, actually goes through that, because actually all information about I and A is sent through this line. But someone could say this is only possible because this map now can act differently if it's first than if it's not. But in order to be sure this second map knows that it's not first, it has to avoid the input here, which tells this map it's first. So let's say there's a particular symbol, as I said, the 0 symbol, which says you are the first map. Now, if this map would sometimes output the 0 here, then things would go wrong here, because this map would act completely wrongly in this PR box example. But in order to satisfy the unitality condition, you sometimes need to give it that in a certain sense, because the input is sometimes that, and it has to do with that. But to be honest, I don't have the way we found it was really via information theoretic considerations, which was you write it equivalently as something else, and you find that in the paper. There are some circuit diagrams, and there you see which information about certain parts, which systems should contain sufficient information to recover the information from there. And by looking at these, you see that there's something missing in a certain sense. And then, so actually you see that this X can screw up the K too much. So, okay, one, let's say, a more technical explanation is, at some point in the proof, you need to compare the Choi-Minkowski representation of this whole system with the Choi-Minkowski representation if you only start from here. Now the Choi-Minkowski representation is constructed by considering basically a uniform input, which is then, of course, purified by the reference system. And so it's in order to compare the Choi-Minkowski representation of only this with the Choi-Minkowski representation of the total thing, you need somehow to ensure that the input that what arrives here, if you give a uniform input here, is still a uniform input so that the two representations can be compared. So if you really think of Choi-Minkowski on this level, you put something uniform here when you want to represent that. And now you want to compare it to the representation of when you start here. And in order to facilitate this comparison, you need to make sure somehow that here it's still uniform. So that is a more technical reason. That's maybe not a good intuition, but that's at the end how we basically arrived at it. So this is really the technical reason. So if anyone has a good intuition, like I wish I could answer this question in a satisfactory way, and I cannot. It's somehow still a rather technical thing. I'm also not sure whether it could be weakened. I mean, as I said, there's a converse statement, but the converse statement just says if there are maps such that they're unital, but this doesn't mean that unitality. So it could, for example, be that that if you have here maximal support on the input, it has to have maximal support on the output. This could be something potentially sufficient, something like that. So this is something that is an open question. Let me maybe in this context mention the other. So this is one open question, how to understand the unitality condition in a more operational manner, and I don't have the answer. The other open question is this whole thing robust? So if this condition here holds only approximately, is it then still true that this holds approximately? And this would be particularly important for people I talk to who work on quantum gravity, because they're saying the commutation, it's very natural to say we somehow want to weaken the commutation condition. And now we have some hope because the commutation condition is now connected to an actually very nice information theoretic measure. So you could say, what does it mean to weaken a commutator? That's not so clear. You have to introduce some absolute or some norm of the commutator, but this has, for me at least, not a well-defined operational meaning that I ever was convinced about. But if you say, okay, now we can express this commutation together with the unitality as some conditional mutual information, this is a very natural way to quantify non-commutativity, the amount of non-commutativity. So the hope would be that if you put here an epsilon, then this statement is still true. This is a very difficult problem, it seems, because it requires to generalize the result by Haydn, Petz, Chose, and Winter to the non-exact case, which, as far as I know, has only been done partially in a certain sense. And so I think it would be extremely interesting to do that, to just ask, here we have something like this, and then the question is, does here this factorisation here, like this thing, also hold approximately? And I think that would be important for many applications as well.
I think Lucien had a question quite early on.
Yes.
So it would be natural to consider the case where the K coming out is different from the K going in, especially since the system A could take away some part of the Hilbert space.
Mm-hmm.
But then that seems to block you considering this.
Yeah.
Do you have any thoughts on that?
Yeah. So as I said, we have this project we are working on space-time correlations where this problem arises. And in this case, it actually indeed, what happens is that somehow the natural maps we want to consider are maps where something from K is taken out of K and put into A and no longer here. And so in order to map it to this type of problem, what this thing then does is just it replaces the missing A here just by some maximally mixed state or something, so just by some dummy thing. So that's how so this is just to say this is indeed very natural what you're suggesting, and the way we think of this is just if you take information out of the system, you just have to, I mean, that's in a sense fine, you can just leave it there and replace it by a dummy thing, but I mean, it doesn't matter what you replace it with, because usually this thing will just not act on that part.
So then your theorem statement would go through even in the case where you have something different coming out.
Yeah, so I would say there is we don't have a formulation of anything more general in that direction, but I would suspect that if you indeed make this space small and say instead we can here put some extension map, which somehow just like a recovery map in these that somehow just replaces this by something else. Then and then this condition has to hold that this could still be true. Yes, that's also an interesting direction to go, but we didn't so far. I mean, this is a pretty new thing, so actually we haven't explored any of the directions that were now suggested, nor the open questions. Yes, it was in August, yes.
One question at the back.
So this is, I guess, sort of stemming from a short Markov chain condition. So if I take the algebraic decomposition and then I trace over K, I wind up with a separable state between the AI tilde and the BJ tilde registers. So then, can't I just connote that index of the separable state to get like a fully classical common cause? Like in this, like are these conditions actually saying I always have a classical way of getting this map? Am I missing something?
Yeah, so no, I think this intuition is correct, but one has to distinguish between the map, which has indeed this classical decomposition, and the input state, which can still be a quantum state. So in a sense, what you're saying is true for the map itself, which is the thing that is represented by the Joy-Markovsky isomorphism. So the way the map factorizes is indeed somehow that the map is a sum of product maps. So that's probably what you're saying. But now the input to the map in general, which we don't make a statement about, could still be, for example, something that after this doubling map will be a Bell state, for example. So so it's not true that if I now look, so what is true is that the map itself has this distribution, but if I now cut here and ask myself what is the state here on the 2K systems, then this could be an entangled state still.
Okay, that makes sense.
I think we had one question in the third row earlier. Not you.
No, Ellie.
Ellie, okay.
Just to sort of follow up on what Rob was saying, I appreciated your explanation of unitality in terms of being able to do analysis with the isomorphism. But if I think about how you cheat to achieve the PR box, you achieve it with sort of causal signaling, where sort of the intermediate state passed from the X map to the Y map has information about I. Right? It's a different state. So I'm thinking if you relaxed unitality and you said, for all sigma I, when you trace out A, you get the same final state on K. For identity. It doesn't have to be the identity on K, it's just the same final state. So there's no signaling condition. Now, unitality implies no signaling, but no signaling doesn't imply unitality. What this would allow, though, is it would allow like knowledge of which party came first. But even unitality still allows some knowledge of which party came first, because I can consider like
some probabilistic knowledge.
Like a rotation on Z or rotation on X, which
right, yeah.
I think. Although you haven't proven it, do you have any intuition as to like that would not be a sufficient condition, or that would be a sufficient condition?
Yeah. So maybe I'm afraid I have to give the same answer as to Rob. I wished I had a good answer, but to me, the unitality condition is on the one hand, depending on how I think about it, surprisingly weak, because as I said, it somehow doesn't completely avoid like the transmission of information from one to the other. But on the other hand, it sometimes seems again...
It doesn't reveal any information about I, which is a really strong condition.
About I, yes, but that it doesn't about I is in a certain sense already captured by... yes. So, I mean, it's... Okay, I have to think whether it doesn't about I, because in principle, no, it can still convey... It can make things that depend on I. I mean, this just says if the other thing is a completely mixed state, then this is mixed. But somehow there could still be some action that X performs on K that depends on I. So that's not... so I don't think it's true that somehow it cannot depend on I. So that's why I'm sometimes surprised how weak it is, and sometimes, again, think it's actually still hard to justify operationally. So
for different...
Yes. For example, you could just... For example, any unitary is, of course, unital. So if you do a conditional unitary on K, whatever it is, but you conditioned on I, then that still satisfies this condition, yes. So that if you think in that way, it's again somewhat surprising that it works, but yeah, I don't know. Okay, but thanks for the many questions.
Do we have any more questions? If not, then I have one question. So, can you say anything about the decomposition of the tensor product of k prime and k double prime? Does it decompose in some nice form like tensor direct sums of subsystems?
So, I mean, actually the way the proof works with this is that first of all you get a decomposition of k in the same way as in this result by Heiden et al., where you say, okay, the k itself is somehow decomposed into something like ki on the A part, let's say, kb. A. So a priori you have something of that type. And then what we are doing because what we want is that here the x is the same x as here. And so if you would just, somehow it cannot be that you just give these systems to that because this is too small. So what we do is we embed these again into k and this as well into k. I mean, into some system which I call k prime and k prime prime, but they are isomorphic to k. Yeah. So I'm not sure this answers the question, but the a priori decomposition of k that is naturally comes out of the proof is actually such a decomposition, and then we just do an embedding which basically says we can again see that part as part of the larger space where we just fill up the rest with some identity states, I mean with some maximally mixed states, and so that then gives the explicit construction.
That's very interesting because there's this framework that me and Nick and Robin Lorenz in Oxford are working on, and there is a result there that any tripartite box that doesn't signal from the rightmost to the leftmost and leftmost to the rightmost can be decomposed in terms of two tensor product boxes with some pre and post processing, which has wires into both, that's decomposed in a direct sum.
Oh yes, right. So Villasini has told me about this result. Yes, yes,
exactly.
Yes.
But in that result, it was not completely clear that. So when you write the two boxes as x and y and yx like this, I think in that result, those two boxes x and y were not explicitly the same x and y that you've written as a tensor product. So this looks like a even stronger result in some ways.
But yours was the result where these maps are unitary channel, unitaries. Yes, right. Yes, no, I've actually,
Here they are not x and y. Yes, they're CPTP maps, exactly.
Yes, right. Yes. Yeah, actually, when I first saw that, actually, I mean, we had this result, and then Villasini told me about yours. Then I thought, oh, maybe we could have gotten our result as a corollary from yours by just looking at the Stein spring dilation. Yeah. But this doesn't work because the Stein spring. I mean, if this is true for the completely positive map, it's not true that for the Stein spring dilation of these maps, this is still true. Right. So that's why it's actually not in that sense related, and that's why I'm also, I mean, it's related in the question, but I'm not sure therefore whether one can transfer the specific decomposition into your setup. But maybe, I mean, that's a possibility.
It looks like it's even more specific here that the same x and y appear in both.
Right, yes, yes, right.
Unitary
yes.
Result. But
yes.
I'll have
we can discuss that, yes.
Yeah, we can discuss that.
Okay.
By the way, I think the result that Claire just mentioned about the decomposition in the case of unitaries, I think that's going to be closely related to the significance of this unitality condition and to Rob's question earlier, because the vanishing of that conditional mutual information is equivalent to the availability of some Stein spring dilation of that whole circuit. Okay. In which, so in this circuit that we've got that isn't Stein spring dilated, it's the case that K is the only thing that signals to both A and B. But the vanishing of the mutual information is equivalent to the availability of the Stein spring dilation, such that even in that dilation with those extra systems, it's still the case that K is the sort of complete common cause, if you like, of A and B. And yeah, in the case where that Stein spring dilation is available, I think you're definitely going to be able to have that factorization. So it seems like somehow the unitality condition
that would be interesting. Maybe
this type of Stein spring dilation is available.
Okay, yeah, I'll have to, because it would be great to have more insights on what that exactly does on a more operational level as well, but maybe just that could be a hint on that.
Thanks.
Yes, yes, and I mean, the other thing is one could also think about this condition again in terms of this update rule that I mentioned before, because that's often not, that hasn't, at least to my knowledge, not been considered so explicitly, the importance of that rule. And one could now ask the question you ask, is it actually necessary to have that update rule or not? That would be kind of a special case of that question of the significance of the unitality condition in the classical case. I mean, the case where A, B, I, and J are classical. And already that question is to me not obvious. Like, what's the most general condition on the measurement such that we have that? And maybe it could be useful to start with that to get a better intuition.
Could it be like intuitively we do something like if I compute the average CP map that the instrument defines, then it's a Hermitian superoperator. So I take you know, the dagger relative to the Hilbert-Schmidt inner product.
Yes.
It's the same, and that means because it's trace preserving, it's also unital.
Yes. Okay, I see what you mean. Yeah. Yes. I mean, cool. Yes.
Okay.
Yes.
So,
Okay. Let's discuss this further. So thanks a lot for the many questions.
Exactly. So I think maybe that's it for questions now. So I think we can thank Renato for a really nice talk again.
Okay, thank you.